Richard Feynman walks into the lecture hall without ceremony. No dramatic pause, no formal introduction, just a man carrying a piece of chalk, smiling like someone who knows a secret the universe is trying very hard to hide. The room is filled with students, scientists, skeptics, and curious minds who all share the same silent hope that today, finally, quantum mechanics will make sense. Feynman looks at them and says, "Let me be honest with you from the beginning. If you think you understand quantum mechanics by the end of this talk, you're fooling yourself." Laughter breaks the tension, but the warning lingers in the air. He turns to the board and draws a simple, straight line. For most of human history, he says, we believed the universe worked like this. Clear causes, clear effects. Objects exist in definite places with definite speeds, doing definite things whether or not anyone is watching. He pauses, then wipes the line away. But nature, he continues, doesn't care about what feels reasonable. Quantum mechanics, Feynman explains, was not invented because physicists wanted reality to be strange. It was discovered because reality refused to behave. At very small scales, atoms, electrons, photons, the universe stops following the rules our brains evolved to expect. The equations work perfectly, predictions are accurate beyond imagination, yet the meaning behind them remains deeply unsettling. He draws a dot on the board. This is an electron, or at least this is how we pretend it looks. The problem, he explains, is that electrons are not tiny balls. They are not little planets orbiting a nucleus. They do not travel along neat paths. Asking where an electron is before you measure it is like asking what decision a coin has made before it lands. In quantum mechanics, particles are described by a wave function, a mathematical object that does not tell you what will happen, only what might happen and with what probability. The universe, at its deepest level, is not deterministic. It is statistical. Then Feynman reaches the heart of the madness, the double-slit experiment. Electrons are fired one at a time at a barrier with two slits. Behind the barrier is a screen that records where each electron lands. Common sense demands that each electron must pass through one slit or the other, but the results disagree. Over time, a wave-like interference pattern appears, as if each electron passed through both slits at once and interfered with itself. The room grows quiet. Feynman explains that this is not a trick of instruments or a failure of measurement. When no detector is watching the slits, the electron behaves like a wave, exploring all possible paths simultaneously. But when a detector is placed to observe which slit the electron passes through, the interference pattern disappears. The electron suddenly behaves like a particle, choosing a single path. The unsettling conclusion is unavoidable. The act of measurement changes the outcome, not because human consciousness magically alters reality, but because measurement itself forces the quantum system to abandon its many possibilities and commit to one result. Before measurement, the electron exists in a superposition, a combination, of all possible states. After measurement, the wave function collapses into a single outcome. Quantum mechanics does not describe reality as it is, Feynman says. It describes reality as it reveals itself when questioned. This leads to another deeply uncomfortable truth. Particles do not have definite properties until they are measured. An electron does not have a precise position and momentum at the same time. This is not due to experimental limitations. It is a fundamental rule of nature formalized in Heisenberg's uncertainty principle. The more precisely you know one property, the less precisely you can know the other. Reality itself enforces this limit. Feynman emphasizes that this is not philosophical poetry. It is a mathematical fact confirmed by every experiment ever performed. The universe does not allow complete certainty. Then he moves to one of the strangest consequences of quantum mechanics: entanglement. When two particles interact, their properties can become linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, disturbed by the idea that information could appear to travel faster than light. yet experiments confirm it. The universe at its quantum core is not locally separable. Particles that were once connected remain connected in a way that defies classical intuition. Quantum mechanics does not break the speed of light, Feynman explains, but it does break our assumptions about independence and separation. As the talk continues, Feynman strips away one comforting illusion after another. There is no underlying clockwork reality hiding beneath quantum randomness. There are no hidden variables restoring certainty. The equations say what they say, and they work. Nature is absurd, and we must accept it. He points out something even more unsettling. Quantum mechanics does not describe particles moving through space in the way we imagine. Instead, it describes probability amplitudes summing over all possible histories. An electron traveling from one point to another explores every conceivable path. Straight lines, curved lines, loops, even paths that go backward in time, each contributing to the final probability. Reality at the smallest scale is not a single story but a vast collection of possibilities interfering with one another. The audience struggles to keep up, but Feynman reassures them that confusion is not failure. Confusion is the correct response. Quantum mechanics is not weird because our explanations are bad. It is weird because the universe is weird. He reminds them that despite all this strangeness, quantum mechanics is the most successful theory ever created. It predicts the behavior of semiconductors, lasers, transistors, atomic clocks, and the entire foundation of modern technology. Every smartphone, computer, and medical scanner exists because quantum mechanics works, even if no one truly understands why it works the way it does. As the 22 minutes near their end, Feynman offers no comforting conclusion. He does not resolve the paradoxes or restore common sense. Instead, he leaves the audience with a challenge. Nature isn't classical, he says, and if you want to understand nature, you have to let go of the idea that it owes you clarity. Quantum mechanics does not tell us what reality is. It tells us how reality behaves when we interact with it. The universe, at its deepest level, is not made of things but of probabilities, relationships, and outcomes that only become real when forced to choose. Feynman puts the chalk down, looks at the room, and smiles one last time. If you feel uncomfortable, he says, good, that means you're starting to get it. The lecture ends, but the confusion does not. And that, Feynman would argue, is exactly how it should be.